Chapter 7, Lagrangian Dynamics. In this chapter, we'll look at contributions to physics made by the French physicist Joseph Louis Lagrange. It provides an alternative formulation to the standard approaches using forces or energy. The two founders of calculus, Newton and Leibniz, were contemporaries and had a different approach to applying calculus to physics. Newton's first law says that the natural state of a particle is to maintain its constant momentum. Newton's second law says that the time rate of change of the momentum of a particle is equal to the net force applied to the particle. Thus, Newton's formulation of physics is around forces and how they change the motion of the particle. Leibniz took a different approach. Leibniz said that free particles maintain their vis viva, or in other words, their life force or kinetic energy. So Leibniz's formulation of physics was that of energy, whereas Newton's formulation was originally in terms of forces. So these two thinkers laid down the foundations for thinking about physics problems in terms of either forces or energy. Many problems can be formulated in terms of either forces or energy. Each provides advantages in different circumstances. So forces are nice because you can visually see how the forces are acting on the particle through free body diagrams. Energy is a more abstract concept. So in that sense, forces are easier. But because they're vectors, often the force equations can produce more complicated systems of equations than dealing with energy, since it's a scalar. Also, in order to follow the motion of an object, one must know all of the forces acting on the system. So, for example, if you imagine this roller coaster spiraling around this track, one can imagine that it would be pretty difficult to know all of the forces acting on the roller coaster through the track. So knowing the motion might be a fairly complicated thing to do. The equation of motion derived from forces give the full trajectory of the particle. When energy is used, the standard solution usually only gives the speed of the particle and not the direction, because the equation of motion depends on the velocity squared, so only on the magnitude. And finally, here's what the equation of motion looks like. So when one uses forces and one's using F equals ma, you can solve for the acceleration of the particle as the net force divided by the mass. When one uses energy, one can simply use conservation of energy, saying that the total energy is the kinetic plus potential energy. Again, many problems can be solved using either approach. In this lecture, we're going to look at a third approach. And this approach is a result of variational calculus, which is discussed in Chapter 6 of your textbook. We're simply going to give an example of variational methods and then proceed to the result or to the method that we can use for solving problems. So an example of variational calculus is Fermat's principle. Fermat's principle states that light travels along the path that takes the least amount of time to go between 2 points. For example, if we had 2 points A and B in free space, one might imagine that light could take a variety of different paths in going from one position to the next. So it might take this path, or it might take a little bit longer and go this path. Fermat's principle says, again, that it takes the path that requires the least amount of time, which, as we know, is a straight line. So variational calculus lets one solve for the trajectory of, say, a light beam using this kind of a global constraint that of all possible paths, light will take the path that takes the least amount of time. So if we apply Fermat's principle to an air-water interface, we can derive the trajectory of the light beam through air as it refracts into the water. So we can find a relationship between the angle theta 1 and theta 2 between the ray in air and in water. A final result is trying to find the trajectory of a light path through curved spacetime, which might happen in, say, general relativity due to the bending of space around a massive object. So if you have a non-Euclidean or curved spacetime, you can derive equations of motion for light through this curved space. And again, you can do that through variational calculus methods. All right, so we're not going to derive Lagrange's method from variational calculus. That was presented in Chapter 5. We're just going to jump to the final result. The way this works is we're going to define a new quantity, which you probably haven't seen before, called the Lagrangian. The Lagrangian is given by this fancy script L, and it's equal to the difference between the kinetic and potential energy. So, remember that the total energy, E, is just the sum of the kinetic and potential energies. The Lagrangian is the difference, so the kinetic minus the potential energy. Once one has defined the Lagrangian for a particular system, you can derive the equation of motions by applying the Euler-Lagrange equation. So the Euler-Lagrange equation says that the total time derivative of the partial of the Lagrangian with respect to the velocity is equal to the partial of the Lagrangian with respect to the position. So why is this approach useful? Well, first of all, it's based on scalar quantities. So it depends on the kinetic and potential energies, and so therefore you don't have to keep track of complicated vector components of forces. Secondly, it turns out you don't need to know all of the constraint forces in order to solve for the dynamic. So if you have a particle, say, moving on a roller coaster track, you don't need to know, say, the normal force between the roller coaster and the track in order to follow the motion. And this simplifies things a lot when there are complicated constraints present. The one caveat, though, is that this approach is really best applied to cases where energy is conserved. So if there's friction or drag forces present, the Lagrangian method is probably not going to be very useful. So let's look at a simple example. So let's see how we could derive the equation of motion for a simple object of mass m that's in free fall subject to the force of gravity. We know, of course, that the equation of motion is simply that the acceleration is equal to minus g. We're going to apply the machinery of Lagrangian dynamics to this problem. This is going to be a lot of work to get a very simple result, but at least it'll show the method. Lagrange's method is really more practical for more complicated problems. So let's first define the kinetic and potential energies of the system. From these two things, we can easily calculate the Lagrangian. So we see that the Lagrangian for the system is 1/2 my dot squared minus mgy. We'll now take the Lagrangian and plug it into the Euler-Lagrange equation. So let's start calculating the derivatives. We'll start with the partial of the Lagrangian with respect to y. The first term in the Lagrangian only depends on y dot. So the partial of this term with respect to y is 0, since there's no explicit y's present. when you take the partial derivative with respect to y dot is treated as a constant. The second term does have a y in it, so when we take the derivative of m minus mgy, we just get minus mg. Let's now take the derivative of the Lagrangian with respect to y dot. Now the second term goes to 0 since that doesn't have a y dot. If we take the derivative of this first term with respect to y dot, we get 1/2 times 2 my dot. The 2 cancels the 1/2. So to save space, we'll just show the result. And now we'll take the time derivative of this result. So the time derivative of m times y dot is just my double dot. If we combine these two results, we simply plug this first result is the right-hand side of the equation. This result down here is the left-hand side of the equation. We get my double dot is minus mg, and we now see that this is just mass times acceleration is equal to minus mg, something we could have written down very easily just using forces. We can, of course, simplify this a little bit to say that the acceleration of our particle is just minus g. So again, we've taken a lot of effort to derive a very simple result that you already knew. But this approach, or this formalism, is very powerful, and it will let us solve much more complicated problems. Let's look at another simple problem that is a mass on a spring. We'll go through the exact same procedure for this. So again, we'll start by writing down the kinetic and potential energies and then calculate the Lagrangian. So the kinetic energy is 1/2 mv squared, and the potential energy is 1/2 kx squared. We can combine these to find the Lagrangian. So we see that the Lagrangian for this system is 1/2 mx dot squared minus 1/2 kx squared. To find the equation of motion, again, we'll plug this into the Euler-Lagrange equation. We'll calculate the partial of the Lagrangian with respect to x. Again, we see that the partial of x dot with respect to x is just 0. X dot is treated as a constant. So we just take the derivative of the second term. We get minus 1/2 times 2 kx. The 2 cancels the 1/2, so we get minus kx. We'll now calculate the partial of the Lagrangian with respect to x dot. Again, the second term will go to 0. The derivative of the second term will go to 0. The first term, when you take the derivative with respect to x dot, we get 2 times 1/2 mx dot. The 2 cancels the 1/2. And we get mx dot. Taking the total time derivative of this expression, just gives us mx double dot. Combining these two results tells us that the mass times acceleration of the object is just equal to minus kx, and this we see as just the restoring force of the spring. So again, we get a result that's that we already knew, but at least it's reproduced something, so we are starting to trust that this method is giving us the correct answers. We can, of course, rewrite this equation in a more standard form. In the next section, we'll see how we can generalize this method to other problems that have complicated constraints that might be a little bit harder to solve using energy or forces.